Okay, good morning. We are on lecture 16. I guess you're all doing the homework too, right? The X-foil homework. How's it going? Any questions? So if you haven't started, you really should start now. It's all pretty straightforward, but if this is the first time you're using X-foil and trying to figure out all the different files and how to plot and all that, there will likely be some issues in the beginning, right? Once you get familiar with it, it'll start rolling pretty nicely. Yes.
Can you talk a little bit about how to format the reference columns? Like I know we have these example ones, and I've been comparing them to what we were given for problem 2, but if you could clarify how those are formatted, that'd be great.
So reference files are the ones in which you put, for example, reference, lift, drag, alpha, CL, CD, CM data, for example, from experimental data or from some CFD code with which you're trying to compare X-foil results. So the way that works is the p-plot will do plots like this. Something like this, right? It'll be, let's say your X-foil curve is like this. And if you plot wind tunnel data, you might plot it as points and maybe it'll look like this. And then you'll have some pitching moment curve, and that might be like this. And then depending on whether you have this or not, you can, so sometimes you may not have pitching moment, you might have only these things. So the format for that should be described in the X-foil user guide. Oh. So there is a user guide somewhere, right? X-foil, maybe down here. Yeah, xfoil.doc.txt. Let's download that, or let's just look at it here. And I believe if you search for reference, yeah. So this is the part where the user guide tells you how to format the reference data. P-plot permits reference data to be overlaid. The reference polar data has the following form. So that's all it is. You tabulate CD versus CL data separately. Then you put this 999,999 to tell p-plot that data set is over. Now you're going to start putting alpha versus CL, then 999,999 alpha versus CM, and then if you have transition data, you put XTR over C versus CL. So the reason for doing it this way is experimental data is not always the data sets. So it's not always like CL, alpha, CL, CD, CM. So at the same alpha, you may not have CL and CD. That's because depends on the experiment really. They might actually get lift data in one experimental run, and then they might get drag data in another experimental run. So the alphas at which you have CD may not correspond to the same alphas at which you have CL. So it's just better to, well, I guess you can't see what I'm doing. So experimental data is not always like this. And that's the reason why pplot uses this format, I think. So this gives more flexibility. Okay. Any other questions? Yes.
There's one, I think it's on question 3, where you ask us to compare different pressure distributions for different angles of attack. So it doesn't specify like how many angles of attack you want or anything like that. So I forget how the question's worded exactly. Problem 3.
Okay, let me see if I can pull it up quickly. Oh, it's in Moodle. Question, which one?
3. Or yeah, using CP distributions for tier depending on the
So,
value of CL.
So this is important. Using CP distributions at different values of lift coefficient.
Yeah.
We've talked about how when you compare two different airfoils, if you compare at the same angle of attack, that doesn't necessarily make sense. You should compare at the same CL, because let's say in NACA 2412 at 5 degrees may have a very different CL from some NLF airfoil at 5 degrees, right? So when an aircraft is flying at a certain speed, that corresponds to a certain lift coefficient, not angle of attack. So compare the two airfoils at different values of CL. I'm going to let you choose the values of CL. Okay, so you can see how the polars look and where the polars differ, and maybe select those CLs in your discussion.
Okay. Do those need to be co-plotted or just like?
Yes, don't put them side by side. So this sort of thing, it's best to extract the CP out, go to the documentation and see how you can write the CP out to a file, and maybe use MATLAB to plot. Don't just do a screen grab of CP of one airfoil and another airfoil and put them side by side. You really can't compare things clearly like that unless you co-plot them. And I don't know if Xfoil, I don't think will allow you to co-plot CP from two different airfoils. So write out the CP to a file, use MATLAB to plot them. And of course, when you plot CP, plot it the correct way, which is upside down, negative going up in CP. Otherwise, it'll just look weird compared to everything we have been discussing. Yes.
In problem number 5.
Yeah.
Can you tell us what CMC by 4 has to be achieved? I mean, is it related to the question part A? Or
Yes. Approximately the same CMC over 4, which means same as what you get in part A. Okay. Any other questions? I think there was some other question you brought. Yeah, go ahead.
I wanted to ask about setting up a batch file to run pplot.
Yeah.
I've been kind of struggling through that. I'm not too sure how to write that. Just because when you open pplot, it wouldn't run the rest of the commands in my file. It would just like, when I close pplot, then it would run a bunch of commands. So I was wondering how you write the file.
You do it exactly the same way that you do for Xfoil. I guess for Xfoil I've given you batch files so you can modify them. But pplot, you essentially, you open a editor and you open pplot and you go through all the motions in pplot that you normally would, right? You would first load up some Xfoil Polar. So you'll say 1 and then Polar file name. And as you're doing that, go to your editor and write those commands one after another. And in pplot or Xfoil for that matter, if you hit an enter, that's like a blank line in the batch file.
Okay.
So at the end of all, you do everything all the way to the end till you close pplot, and you do that also. Like, what do? You do 0 or something to close it? Yeah, so you put 0 there. Then the next time you just go and say pplot less than the batch file name, and it'll just go through all of those as if you were typing it one by one.
Okay. I was trying to open pplot straight from the directory, and so just run a batch file in the directory to open pplot and do it all. So instead of opening pplot with the less than, so that was one mistake.
You were trying to open it with a double click?
No, with just like the first line of the batch file was pplot. So it was,
Oh, right. Yeah. It's you start pplot in your command window and then say use all these commands from inside that.
okay.
Yeah. Just like in Xfoil batch file, you don't put Xfoil on top, right?
Okay.
And then I think you brought up this thing. So sometimes you may find that okay, I'm just going to draw the lift curve. So you may find your something weird like this happening, right? This may be because here's what happens. So when you run Xfoil, and let's say especially if you're using a script file and you're creating some, let's say file1.pol polar, right? So it'll write this out. Next time let's say you make some small modifications and you run this Xfoil and create the same polar file. So Xfoil does not, looks like it does not overwrite the earlier file. Suppose you say file1.pol again, and this file is still there in your folder. Xfoil will not overwrite it. It will actually append to the file. And so let's say, for example, if I think this is what happened with you, right? So if you take my script files where I have run Xfoil some years back with an older version, and I don't know what it's called. I'm just going to call it file1.pol for now. Now you take all of my files and run my script file in the same folder, and my polar file is still there, right? I gave it to you as an example. If you run Xfoil again, my script file will create this file name, but it'll append to it. And you will probably be using a newer version of Xfoil, so things have been improved, right? So these set of points may be corresponding to what I gave you what I generated long back with the old version, and these set of points are your new Xfoil run, but those are both in the same file. So Xfoil will sort through an increasing angle of attack, and it will connect it all with the same line. So it will actually connect the old points and the new points, and it will look all jagged. So the moral of the story is delete the polar file before you do an Xfoil run, because if you use the same file name, it will append to it, and it will plot old data, new data, and everything, and it will look all messed up because of this. Okay, so that's something to keep in mind. So Okay. So let's move on to inverse design methods, and we'll probably start the profile demo today. So in the last class we stopped here with a comparison of two classes of inverse design methods. So single point inverse design methods are where you give the desired aerodynamics, usually the inviscid velocity distribution at a single condition, right? So you will say, essentially, I want this kind of a velocity distribution at a CL of 0.5. And the method will determine the airfoil shape. And performance at other CLs is obtained after the design process. So if you design it for CL of 0.5, and if you want the performance at CL of 1, you just run Xfoil or something like that, and you will get the performance at other CLs. Multi-point design methods are different in the sense that even in the beginning, when you give the inputs, when you give the desired aerodynamics, you give the desired aerodynamics at multiple CLs right away. Normally the way that's done is you divide the airfoil, which you don't know yet, right? You're still designing the airfoil, but you say the upper surface of the airfoil I want to design for high lift condition, high alpha condition of, let's say, 1, CL of 1, and the lower surface I want to design for a CL of 0.2 as an example. So you're dividing the airfoil that you want to design into different portions. Each portion you give the aerodynamics at a different CL. And that actually makes a lot of sense, as we'll see shortly. So in addition to just the advantages of multi-point methods, there are some issues with single point design methods. So let's see what they are. So one of the difficulties is it's often difficult to say this is the velocity distribution I want. It's not just, I've been sketching velocity distributions throughout this course, but that's okay, that's just a sketch. If you want to numerically give a velocity distribution and say this is what I want, to give a sensible and correct velocity distribution is actually a hard thing. So often it is difficult to prescribe an entire velocity not every velocity distribution will result in a realistic airfoil shape. For example, people have found out early on some velocity distribution plots will result in a crossed airfoil. So for example, you could get velocity distributions that mathematically will end up generating an airfoil shape like this. I mean, mathematically it will work. Conformal mapping will do all the, it will chug through all the equations and the airfoil will look like this. So even the latest 3D printer will have problems making this. It's not a physical airfoil. So again, several decades back, people found out that velocity distributions need to satisfy some constraints. And then you really don't know what the stagnation point location is. So when you have to give an entire velocity distribution, that also means you have to say where the stagnation point is. And guessing the location of the leading edge stagnation point is difficult. So in spite of this, there were single point methods, and there still are. In fact, Xfoil has got some sort of a single point design method in the menu called QDES. So it's not really a method where you give the entire velocity distribution, but you can take an existing airfoil and get the velocity distribution out of it, and you can go to QDES and say, move this here, move that here, and you can do that. But then multi-point methods give more flexibility, and there are different camps, just like in any kind of design when you go and talk to designers for anything like cars or airplanes or whatever, everybody will have their own method, and after some time when people get to a level of proficiency with their way of doing things, they just know how to work around the limitations. So there are people who probably use single point methods, and they've just figured out how to do it well, even though there are limitations. But the way we are going to do things in this course is use a multi-point inverse design method. So the motivation is there is a desire to control the airfoil performance So ultimately, the reason you're designing the airfoil is for some aerodynamic performance. Agreed, you still need to put structure inside the wing, and so the airfoil cannot be infinitely thin like a flat plate, for example, in a realistic airplane design, and you need certain space for fuel or actuators or whatever, all those things. So there are still geometry and structural constraints, but for the most part, aerodynamics is what drives the airfoil design. And we know that airplanes don't fly at one single condition all the time. They have to climb, they have to take off, they have to cruise, they have to land, they have to go long range, long endurance, so on. So we want to be able to control the airfoil performance at several conditions, several flight conditions. And when you're talking about airfoils, the operating conditions are usually dictated or thought about on the drag polar, CL versus CD. So an NLF airfoil, for example, may have a drag polar like this. Okay, so you may have different operating conditions right here. So this may correspond to some sort of efficient cruise condition. Something like this may correspond to a climb condition. Maybe this will correspond to a fast cruise condition. And this may correspond to some other condition, like maybe faster than your maximum cruise speed, something like that, right? So it turns out that you want to design the airfoil so that you have some control at all of these conditions right from the initial design stage. So single point designs, on the other hand, will let you tweak the design for A, but then what you get at C you don't know. You have to go and analyze the airfoil with X-foil, and then you'll say, oh, this is what happens at C and I don't like it. Then you can design for C and then you lose A, something like that. So those kind of things can happen. But multi-point designs will let you, or at least they give you the capability to try and control all of these things in the first, throughout the design process. So why does that work, or how does that work? So let's now look at velocity distribution. So I'm going to draw the velocity distribution. Again, I'll be using V as short form for V is same as V over V infinity. So this is the, let's say, the inviscid velocity distribution. Okay, so so let's take the upper surface velocity distribution at A. That will probably look like this. Okay, so this may be, for example, the upper surface velocity distribution for A. And at this velocity distribution, you have favorable gradient to maybe 60% of the chord, right? So if, let's say, there's a Reynolds number of 3 million, then at 3 million, this favorable sort of almost zero pressure gradient, right? But it's slightly favorable. That means this airfoil, if it's a clean, smooth airfoil, will have laminar flow all the way to about 60% at this lift coefficient. So this is at condition A, lift coefficient A on the upper surface. And then at condition B, maybe the velocity distribution will be something like this for the same airfoil. And here you're kind of playing around close to stall, or somewhere near high CL, just a little bit below stall. And maybe this part of the airfoil velocity distribution is important, right? So in condition A, this part is important, this portion of the airfoil. In condition B, maybe this portion of the airfoil is important because that dictates how the stall behavior is. And for condition C, it's really this part is dictated by the lower surface, and so lower surface velocity distribution may look like this. I'm just going to sketch here. It's not going to be exact or anything, but maybe it'll look like this. This is for condition C, lower surface, and here maybe this portion of the airfoil on the lower surface is important, right? So these two are upper surface, this is lower surface, and condition D may be maybe more like this. And again, maybe this part is important. So that's the overall thinking behind multi-point inverse design methods. You divide up the airfoil into segments or portions, and you say, I'm going to use this portion of the airfoil to design for lift coefficient of 0.5, this portion of the airfoil to design for lift coefficient of 1, and like that. So that is the thinking behind the inverse design code we are going to use. And now let's start talking about that. So this was developed by Professor Michael Selig at Illinois. He was my PhD advisor, and I worked on airfoils for my PhD. I think I mentioned this earlier. And this code was so initial versions were developed as part of his PhD. At Penn State. But some of the theoretical foundations actually go back even before that. So there was a famous airfoil designer, Richard Epler, in Germany, who wrote this thing called Epler code, or some places it's called profile. Profile is airfoil cross section. So in Germany, I think they call airfoils profiles. So I think the code was called profile. So based on these foundations, this code was used by a lot of people for many years until, I think some people still use it, but it's until maybe 1980s, 85 or so, this was used. And then Professor Selig came up with the profile code, which is used by a few people. I use it, for example, and it's been used in so many projects, but by a handful of people, let's say that. So compared to the Epler code, numerous additional features. Especially there is one thing that's a game changer, and this is this Newton iteration, which is really another name for Newton-Raphson method. So this Newton iteration is used to automate several tasks. So earlier in the Epler code, a lot of things had to be done manually. For example, if you change something, that will change the thickness, and if you change something else, that will change the camber, and if you change something else, it will change the pitching moment, and you have to like juggle all of these things manually. So when you're changing one thing, you have to constantly change something else for thickness, and you have to deal with that. But as you will see in Profile, the Newton iteration, you can set up the Newton iteration to say always keep the thickness at 12%, keep the pitching moment at minus 0.09, keep something else somewhere else, and then you can go and change the velocity distribution, and every time you make any change, the Newton iteration will always go and keep the thickness. It will alter some things to keep the thickness at some value. So that's just makes life so much easier. Anyway, the theory is based on conformal mapping. Which we've very briefly, we talked about what that is. And the main thing to remember is the airfoil. So remember, in conformal mapping, the flow around a circle is mapped to using a transformation to make it the flow around the airfoil, right? So the airfoil and the corresponding circle is divided into many segments. And these segments are what help us set different desired aerodynamics on different portions of the airfoil. So like I said here, in this example, we used 4 regions of the airfoil, right? So these will be called segments in Profile. So let's use a sketch and talk about how these segments look. So you kind of have to think about the circle geometry to some extent and the airfoil geometry together. So let's talk about a circle here. So this is a circle that's used in conformal mapping, and although you won't be actually fiddling around with any conformal mapping, the inputs you give will determine the transformation function that takes the flow around the circle and maps it to flow around the airfoil. And then here's the airfoil. And let's say we are going to divide the airfoil into 9 segments. Okay, so let's draw these segments and then I'll talk about it some more. All right, so so this point maps to the trailing edge. So one of the first sort of misconceptions I have to dispel, which usually this is a question that people ask in a lecture or two, is that it's not like you have these 9 points and then you somehow draw a spline through it or smooth curve through it or something like that. No, that's not at all what happens. These are just ways to demarcate the geometry and take each one. So for example, we'll take this part and say, I want some velocity distribution at a lift coefficient of 0.3, something like that. And then this one will be, I want something else at a lift coefficient of 0.8, right? So these are just ways to divide the airfoil into some regions, and in each region you'll go and say, this is a velocity distribution I want at this condition. So don't think like just because you use 4 segments. So the minimum number of segments you have to have is 4. But just because you use 4 segments doesn't mean it will be a bad airfoil or it will be a jagged airfoil or something. So it's not at all like fitting a spline through a few number of points. So if you have 4 points and fit a spline, it will look really bad. It's not like that. Okay, so it's not, you're not fitting a curve through these points. In fact, the number of coordinate points is independent of the number of segments. So usually we'll have, I think we have 120 points or something as the output. So the the output XY coordinates will be much more than 9. These 9 segments are just for aerodynamic reasons. And the last segment, this point, last segment endpoint. So this maps to the trailing edge, which is what this is. So we always talk about a segment using its endpoint. So for example, this is segment 4. Right? And when you say point number 4, we usually refer to the endpoint. This is just a convention so that we can all talk the same language, right? So segment endpoint 1 is this, because that's the endpoint of segment 1, 2 and 3 and so on. And the last segment, which is segment number 9 here, will correspond to the trailing edge, the lower surface trailing edge basically. And the way this works is, and we won't go into details of this, the airfoil, when it's operating at some angle of attack, in the mapping, in the circle flow, the cylinder will have some flow direction, and the conformal mapping mat will take care of mapping the flow around a circular cylinder to the flow around this airfoil, which is yet to be determined. And every segment endpoint has an angular coordinate with which you say where you want that segment endpoint. So let's take this segment endpoint number 2, and this angle is called phi2. Phi is the symbol for the angular coordinate of the endpoint, and because you have many endpoints, you need to say that is phi2. So phi I is the angular coordinate So as we'll see later, we'll talk about Theodorsson conformal mapping, Joukowsky conformal mapping towards the end of the course. And so the flow, there'll be flow leaving from the rear stagnation point of the circle, and or there'll be a streamline leaving from here, stagnation streamline, and there'll be a streamline also from the airfoil. So essentially this point gets mapped to the trailing edge, sharp trailing edge. Okay, so what is phi 9? So this is phi 2, phi 1, phi 2, phi 3, the angle of these things. What is phi 9? 360, right? It's a gotcha question. You think it is 360, but it's not. And there is no real good reason for that. Blame Epler for that, I guess. So Epler, for some reason, wrote I think his theory can be anything, but the way he wrote his code, the last phi would always be 60, and I don't know why. I think it has something to do with, this was he developed his code back in 50s or 60s. You know, back then people were using punch cards, right, for any computation. There was no such thing as a terminal. You put all your Fortran statements on punch cards, and it'll have holes, and then you feed it into one card reader, and that will translate it to Fortran statements, send it to the computer. So I mean, they had to do things that we can't even imagine right now. But for some reason, he made the last coordinate segment endpoint as 60 degrees. And when Profoil was written by Michael Selig had been using Epler code for many years, and that's how he came to realize how things can be improved. And he didn't want to sort of think about everything in a completely new way. When you're designing airfoils fast, it's like suddenly if you've been driving a car with a steering wheel, right, and suddenly you design a new car, you're not going to put a joystick because, you drive a car certain way. It's something like that. Anyway, so 60 still is the way we call the last segment, and it's very easy to get used to. So it's not a big deal. It's just when you start off with, it's very bizarre. So we'll also stick with 60 as the last segment endpoint. The first and last segments are called the recovery segments. So you can think of these as segments which help to close the airfoil geometry. So if we take this sketch, for example, segment 1, which is this on the airfoil and this on the circle, and segment number 9. which is this and this. These are the recovery segments. In other words, you think about these things a little differently, whereas every other segment, you can actually go and prescribe some velocity distributions. Here you don't, there are some functions that will help close the airfoil, and you have some control over those functions. Basically, that's it. And this will all kind of become clear as we go forward. But all other segments, so for every other segment, you can specify the velocity distribution, or you can control the velocity distribution by specifying this thing called a design angle of attack, alpha star. So this is pronounced alpha star. And this is a super cool concept. I mean, this Epler came up with this. I don't know if other people thought about this before, but Epler was the one who implemented this in a design method. And it's just such a beautiful concept. So let's talk about what this is. The concept of alpha star. This is really the key behind multi-point inverse design. So alpha star is the design angle of attack for a segment. So okay, so for any segment, alpha star is the angle of attack measured from the zero lift line, at which this segment will have zero velocity gradient. So why is this so useful? So we've talked about velocity distributions in quite an amount of detail throughout the course. So we know, for example, some things. We know that on the upper surface, as angle of attack increases, what happens to velocity gradients? So first of all, how do you talk about velocity gradients? You can talk about favorable or adverse, right? So if you take a little region on the upper surface, as you increase angle of attack, what happens? It becomes more adverse. So as alpha increases, always the velocity gradients always become more adverse. We also know that so near the leading edge, velocity gradients, let's say near the leading edge, towards the front part of the airfoil, velocity gradients change more rapidly for a given alpha change compared to near the back part of the airfoil. That's how the velocities suddenly have a peak, right? As you increase angle of attack, there's a big peak in the leading edge, whereas in the trailing edge, they move more gradually. They become adverse, but at a smaller rate. And the reverse happens on the lower surface. So on the lower surface, as alpha decreases, the velocity gradients become more adverse. And velocity gradients control boundary layer behavior, right? More adverse gradient means boundary layer has a hard time staying attached. That's why as you increase alpha, the upper surface boundary layer will separate because it becomes more and more adverse. If you decrease alpha, the lower surface will separate because lower surface gradients become more adverse. So by specifying a design angle of attack and saying at this angle of attack the velocity gradient is 0, you're kind of specifying the borderline in angle of attack beyond which on the upper surface it will become adverse, below which it will be favorable, and flipped on the lower surface. Right? Does that make sense? So we'll see more of this shortly. But essentially you can take a region on the upper surface and say alpha star is 4. That means at 4 degrees angle of attack relative to 0 lift, the velocity gradient will be 0. At 5 degrees it will be adverse, and at 3 degrees it will be favorable. Instead of 4, if you set it to something else, that will be the borderline between adverse and favorable. And basically velocity gradients control boundary layers, and so you're essentially saying at what angle of attack will a segment have the borderline between favorable gradient and adverse gradient. So let's think about what that means in terms of why is it good to talk about angle of attack relative to 0 lift angle. So let's remind ourselves of some definitions. Alpha 0 lift is the alpha 0 L is the alpha for 0 lift. Some books write it as alpha L equals 0, but I'm just going to write it as 0L. Alpha A is the absolute angle of attack. And in some places, especially in some of the papers that I've given, I've called it alpha Z. It's the same thing as alpha A. Some books call it as absolute angle of attack. I've called it as alpha Z, which is alpha relative to zero lift. And this is essentially alpha minus alpha 0L. Right? Alpha Z or alpha A is alpha minus alpha 0 lift. And alpha is the angle of attack relative to chord line. This is what we normally call as alpha. So on an airfoil picture, for example, this is the chord line. And if the flow is V infinity is coming like this is what we normally call as alpha. But because this airfoil is cambered, it's going to have a zero lift direction or zero lift line, and that may be something like this. Right? That means if the V infinity comes like this airfoil will produce zero lift. So the amount of lift that the airfoil produces is proportional to this angle, the angle between the red line and V infinity, not the angle between the chord line and V infinity, right? Because it's a cambered airfoil. So this angle is called alpha Z. Or in some books they call it alpha A. And this is alpha 0 lift. Okay, so now we've seen all this before. Let's plot this in CL versus alpha plot. So maybe this airfoil will have a lift curve like this, and then this will be stall. What is the slope of this from thin airfoil theory? 2 pi per radian. We haven't done the theory yet, but we have talked about this enough that we know that dCl d alpha is, again, it's a good habit to say 2 pi per radian. That way you won't, in a some years from now, if you have to do something with airfoils, you won't use 2 pi and use it in degrees. So 2 pi per radian, it's a good thing to say it like that. And 2 pi per radian is approximately 0.11 per degree. If you convert 2 pi per radian, it's 2.11 per degree. What is this angle? Alpha 0 lift, yes, this is the 0 lift angle. That's what this angle is. And if we choose some alpha, so let's say I choose this alpha. For this alpha I have a certain CL. And in inviscid flow, this line will keep going like this, right? This is inviscid and this is viscous. So as long as you're not too much near stall, a certain alpha will have a certain CL, and so this is the alpha. Alpha is measured from the chord line will be this alpha. And alpha Z or alpha A is measured from alpha 0 lift, and that's this. So because we know the slope is 2 pi per radian, DCL d alpha is approximately 0.11 per degree. You can even think of it as 0.1 per degree if you want to do a very rough calculation. It's 1/10. So that means lift coefficient CL is really approximately 0.11 times alpha minus alpha 0 lift, which is same as saying 0.11 times alpha z. So this is when so if you're thinking about alpha, alpha z and all that in degrees, it's a simple thing to remember. Lift coefficient is 0.1 times alpha z, or 0.11 if you want to be a little more accurate. So that means now it connects, all this connects to alpha star. So when you say alpha star, so by specifying alpha star for a segment, you're essentially saying, you're prescribing the design lift coefficient at which the segment has zero velocity gradient. So alpha star so that's the reason why this is defined relative to alpha 0 lift. And that means, let's say if we have something called CL star. CL star is the design lift coefficient for the segment. Then CL star is approximately 0.11 times alpha star, when alpha star is in degrees. So if some segment has an alpha star of 5, then CL star for that segment will be 0.55. So that means when an airfoil is operating with this alpha z equals alpha star for a segment, okay, let's try to kind of unpack this. So when an airfoil is operating at an angle of attack of alpha z, and let's say that alpha z corresponds to alpha star for some segment, that means the velocity gradient will be 0 for that segment at that angle of attack. So for example, so let's say you have I'm just going to take a 4-segment airfoil just for convenience. So this is 1, 2, 3, 4. This is segment number 2. Let's say alpha star for 2 for second segment is 7 degrees. Right? That means CL star for 2 is 0.77. So let's say you have designed the airfoil like this with this segment as alpha star of 7. Then if you plot the velocity distribution or CP distribution, for let's say alpha z equals 7 degrees or CL is approximately 0.77. So if you plot this, if you design this airfoil and go run it in Xfoil, because Xfoil converts the airfoil into panels, there's a small amount of discrepancy that will happen. But let's say you plot the velocity distribution in Profoil itself, where the velocity distribution is calculated exactly with conformal mapping. Then it'll turn out that this segment, let's say this is at goes to 50% of the chord. So this is 1.5. This segment will have exactly flat velocity, and then it might go to something like this. And the lower surface may be doing something else. So 3 is here, maybe it will do this. But this is the segment we are interested in. This is segment 2. So segment 2 will have 0 velocity gradient when alpha z equals alpha star of this segment. Like that, the alpha star for this segment may be 2 degrees. Then if you put alpha z equals 2, then this segment will have a flat velocity distribution. Which means if you go to slightly more than 7 degrees, this segment will have adverse pressure gradient. If you go to slightly less than 7, it will have favorable gradient. So you can say, for example, that roughly tells you, it will depend on the Reynolds number, but you can calibrate that pretty easily by, if you take this airfoil, run it in Xfoil, and then you make a change and run it in Xfoil again, you'll quickly get used to that. So for example, that's essentially saying you're designing this part of the airfoil to have laminar flow up to 0.77 approximately, right? Plus or minus a little bit. That again depends on Reynolds number. That will define the upper corner of the drag polar. The CL for the upper corner of the drag polar. Like that, if this segment alpha star is 2, the lower corner of the drag polar will be close to 0.2, 0.22, something like that, 0.25. And the details will depend on the Reynolds number, so you always need something like Xfoil. If you run it, then you'll get a polar, and then you can start moving it around by changing these numbers. So we'll talk much more about these things, and we'll start using the code, and I'll demonstrate it with some examples. But that's the general idea, and that's why alpha star is such a sort of beautiful concept when you're trying to do airfoil design. Okay, so we'll stop here today. Thanks.